This lecture we will see about pooling in deep learning, how convolutional neural networks compress spatial information and why it matters for building efficient powerful models. What is pooling? Pooling is a downsampling operation applied after conventional layers in CNNs. It reduces the spatial dimensions, height and width of feature maps while preserving the most important information. It reduces the computation, controls overfitting and builds invariance. Two dominant pooling types are there. One is max pooling and another one is the average pooling. So max pooling select the maximum value in each window, then it captures the strongest features, most common in practice, good for texture and edges. The average pooling computes the mean value in each window, smooth features, retains background context, useful in later layers. How pooling works step by step. So first it has to define a window, choose the pool size, for example 2 into 2 strides, then select and slide and select move window across the feature map, then aggregate, take max or average within each window, output downsampled feature map. Max Boolean, that is capturing the strongest signal. Max Boolean selects the highest activation within each window. This makes it excellent at preserving sharp, salient features like edges and corners, translation invariance and the sparse activations. Average Boolean, smoothing the representation. That is, average pooling computes the mean value across each window, producing a smoother, more distributed representation of the input. It retains the context common in later layers. Key pooling hyperparameters are the pool size, stride, padding, and placement. Pool sizes 2 cross 2, large, typically 2 cross 2. Largest sizes can be 3 cross 3 or 4 cross 4. It compresses more aggressively but recurs loss in the fine grained detail. Stride usually matches pool size. Then padding controls how edges are handled. Placement applied after activation function relu stack in multiple convolution pool blocks builds higher hierarchical features. The benefits are it reduces the computational cost and memory usage, provides translation invariance, assess implicit regularization, expands respective field of deeper layers, prevents overfitting in the early architecture, discards spatial information not learnable, can lose the fine-grained detail in small objects, strided convolution, fixed window size lacks adaptability. Cool in modern architectures, LeeNet, AlexNet, ResNet, and transformers. Downsamplings by design, max versus average, hyperparameters matter, evolve in role. Thank you.